Yeah, thank you very much for giving me the opportunity to speak a little bit about my work here, and it's also obviously a great pleasure to be able to be part of the community and now as a voting member. And I hope that with this, I hope to kind of introduce a little bit about what I've been working on, and I hope that you'll find we can find many common, I guess, areas to work on, and some of this can contribute to the aims of the community. Um, right. So I'll start then. So I'm not sure if everyone actually really knows me, so I thought I'll give you a little bit of introduction about me and my work. So just very briefly, I did my PhD at Guillemar in Kiel, starting 2015 and finished in 2018. After that, I did a short postdoc at the German Research Center for Geosciences in Potsdam. And since 2020, I've been at St. Andrews as a research fellow, and as a last year as a early career research fellow from Liver, whom I got this starting fellowship from the Leverhulme Trust. So broadly, I work on brachiopods, but I'm interested in other biominerals as well, and coral reefs. I work a lot on evaporites too. That's kind of a new direction, and I'm particularly interested in their fluid inclusions and what can they tell us about Earth's past. Um, I employ, I'm an isotope geochemist, so I employ isotopic tools, but I do also a lot of elemental mapping and work on new method development with my students. That you can see a couple of them in the clean lab over here. And obviously, it's once we get these isotopic and geochemical records, it's good to do something more quantitative with them. So I'm interested in modeling as well, and I combine a lot of these data generated from these approaches and with kind of in or into Earth system models. And I'm also exploring kind of machine learning approaches and what can they tell us, or how can they help us understand and refine the data a bit more. Right. So the kind of main research questions deal with the evolution of seawater chemistry. So I look at kind of Phanerozoic timescale evolution of pH mostly, and because pH and CO2 are coupled with that, we can actually get kind of complete information on the carbonate cycle. And I'm also working on kind of bulk composition of seawater, boron, strontium, lithium, and other elements. I do past climate and environmental reconstructions, so again, mostly focused on what can boron-based CO2 reconstructions. And I'm also fascinated by biomineralization mechanisms of marine organisms. So some of the work also goes into trying to understand how, for example, brachiopods build their shell and what that can tell us in turn about the environment. Um, I guess the kind of the main goal is summarized of or the mission, I would say, maybe of some of this research is summarized down here, where you can see the seminal paper by Jan Weitzer published in 1999, and that's kind of what really how opened our understanding of the deep time climate. So that's the oxygen, the initial oxygen isotope record. Jan Weitzer et al. Published. And what you see here next to it is the recent benthic oxygen isotope record by Thomas Westerholt et al. That spans, as you can see, the Cenozoic. And kind of the mission is really to try to make sense out of deep time data so that we can, even for the rock record and times like the Permian, we can start generating this sort of curves. And obviously, that's why I'm here. My kind of special focus is the Permian. I've always been really interested in the Permian and how how it ended, how the Paleozoic ended, but also how the Paleozoic started. So the time span's big. We have to start somewhere. There's lots of work to be done. So I've been working on various times intervals, but loads of my kind of personal interest is in the Permian. Right. So we published essentially this paper in 2020 on the Permian Triassic mass extinction. So I've worked on that, and we've got another record kind of slightly revised coming up. Other thing in the Permian I've been working on most recently. So we kind of learned how it all ended. So now the question how it started is what I've been working on, and my colleagues and my group is how it all started. So trying to understand the late Paleozoic ice age a bit better, and with that the dawn of the Permian. And there is a time in the middle that is not boring at all, and that's something planning on to work in the kind of working on now, and then it's the plan for the near future is to kind of try to deconvolve what's been going on in terms of CO2 and the zeologic chemistry during this time interval. And I hope that some of that work can also contribute or be relevant to some of the efforts in the subcommission that are directed to revising the base Hungarian GSSP and the base Rhodian GSSP. And yeah, it's a real pleasure to be able to be part of these groups. Okay, so a little bit about, just very briefly about the work that we published on the Permian Triassic. So in 2020, this paper came out that showed, provided a boron isotope record of ocean pH and atmospheric CO2. So we measured brachiopods, and boron is a proxy for ocean pH. I won't get into details now. Just remember that maybe there in another seminar I can explain a bit more how that works. And from boron isotopes, once we reconstruct the pH, because CO2 and pH is coupled, we infer the CO2, and essentially we quantified the CO2 during this mass extinction. So you can see a little summary of the data here. I should go back actually, and I should say I was also very glad to see that this work was well received in loads of media. So it generated loads of interest, and there's also a little piece that I wrote on that in Permaphils some time back. Right, so this is the boron isotope record that we made. So it kind of spans the last few hundred thousands of the Permian and the very early Triassic. We've got the characteristic carbon isotope excursion and oxygen isotope excursion during this time interval. I don't think I need to introduce more to this community. The point to say, this is the first really well-preserved deep time boron isotope record that demonstrated that the sort of work people have that's been really kind of taking off in the Cenozoic with forums in the last 10-20 years is actually possible in the deep time. Ever since we've generated a lot more records, and I know also lots of others have been interested in generating these sort of records. So it's great to see that that's looking extremely promising and actually can extend how our knowledge of pH and CO2, beyond the Cenozoic. Anyway, we demonstrated there was a huge boron isotope excursion. From that, we were able to, for the first time, kind of quantitatively derive the pH. And once you know the pH and you have some carbon cycle constraints like the carbon isotopes, you can estimate the CO2. And not only that, we can also think about how much CO2 would have been necessary to produce this event. So we derived the value for 40 times the modern, like everything that's locked in modern reserves currently. Okay, that's a little bit about that. I'm not sure. Okay, I still have a few minutes. So where do we go from here? So that record was really exciting, and we were able to zoom in, and obviously the Permian's big, so the next kind of mission has been how can we go bigger and longer and make something stronger, I guess. So the mission's been to make a robust record of actually whole Permian pH and CO2 and climate since. So I'll give you a little example from the early Permian, but essentially I've been working, again, this is really a team effort with lots of wonderful colleagues and collaborators and students contributing to this work. There's many to be mentioned, but obviously Lucia has been really instrumental in this, and you can also see in picture there Marco, who's done field work and contributed some samples to this. So we've made loads of new measurements, but we've also revised all of the available literature data spanning this time interval. So we've been looking for kind of preservation. So all the data is preservation screened based on trace elements, petrographic approaches. We time calibrated available data and we compiled it. And we added new measurements, and all of these measurements are based on brachiopods. So we generated a new database of kind of Permian data. One person, very important, I forgot to mention, is Claudio Garbelli, who's been also really good collaborator and helped a lot on this. So how do we make what I call, I guess, a robust record? Why do we think our record's robust? So the first step towards this is we're making sure that all of the data we use is pristine. Pristine means there's no contamination from enclosing sediments. So we separate the shell completely, and we look at tracers like aluminum, shown in the panel over here. So aluminum is a big contaminant of elements like boron to samples. So we screen thoroughly for that. We check for preservation. So our data only includes well-preserved brachiopods. Again, we can look at trace elements to give us clues on this, but we've got also petrographic approaches. And then we're also actually calibrating and thinking about not only grouping all brachiopods together, but different brachiopods taxa to account for vital effects. I won't go into details, but if you have questions, please let me know. But we're redoing essentially one of the problems with all of the data that's published that people use it, and often it's not brought to be on the same timeline. So the data's not, when it's compiled, it's not in the same currency. So we're actually revising all of the published data and making sure that our published data are on the same age model. And then for if you want to make a long-term record of CO2 from boron isotopes, you need to know how the actual bulk composition of seawater has changed. I mean, this is in a way the same thing as for oxygen isotopes. If you like to reconstruct temperature from oxygen isotopes, you need to know how the oxygen isotope composition of seawater has changed. So the same sort of issues. So we're looking at kind of ways how to better interpolate the data and how to apply priors. We're applying relatively conservative priors and then bringing together all of it in a Monte Carlo Markov chain Monte Carlo approach. So we're looking at kind of Bayesian statistics to help us with this. That's been recently shown in a paper here. But one thing that's really important, that's really useful for this, is also to get direct empiric measurements of how seawaters change from fluid inclusion. So a lot of my work recently has been looking at fluid inclusion and seeing what can we learn about seawater chemistry from them? How can we best reconstruct ancient seawater chemistry from it? And once we have all of that, this is my last slide, because I think I'm running out of time here, or hopefully just on time. Well, anyway, once we have all of this, we can actually generate records like this. And what you're seeing here is just brachiopod data. There's no bulk rock. There's loads of bulk rock records, but I haven't included them because we can't, as I just told you, we can't really objectively screen for lots of the kind of problems with the bulk rock records. So here you see, it's not full Permian yet. It will be soon, but this is an example from a paper we recently submitted. Here you can see kind of a record of carbon, oxygen, strontium, boron isotopes, and then reconstructing CO2, evidence for glacial deposits and coal forests spanning 80 million years, including the late Carboniferous and the kind of big part of the early Permian going into middle Permian. And you can see how there are loads of gaps in the record still, but you can see how kind of defined the curves start to become once we do this, and especially the strontium curves, really wonderful, and also the oxygen curve. There are gaps, but for example, in the pink here, you can see previous estimates, kind of a previous compilation effort by the FAN-SST project by Emily Judd et al. And then if we just take out the brachiopod data and further screen it, we get something like this. So patterns start to emerge. And then here's our boron data, which is very exciting. It tells a story of the start of the Permian, of a high CO2 start to the early Permian. But I won't get into the details there. It's just it was just an example. I really wanted to show you that if with all of these work and by bringing all of these approaches together, kind of hopefully a bigger and kind of better and more robust records are possible. And I hope that that's something that Permian would be a fantastic starting point, and that's kind of the mission. And I hope that we can work towards this to create kind of records like this for the Permian that can be later also adapted by maybe other subcommissions. And I think I'll leave it there. Well, thank you very much, for listening. This is an actual paleoart reconstruction of how it all started. So this is the late Carboniferous, and this is the dawn of the Permian. So that's how the Permian started, based on kind of really scientific paleo art. Thank you.
Hi everybody, and thanks for inviting me here in this group of stratigraphers. I'm Lorenzo Marchetti. I study tetrapod trace fossils and also other things like stratigraphy, paleoecology, invertebrate traces. And one of my main topics is stratigraphy and biostratigraphy in the Permian, also Carboniferous and Triassic, mostly Permian. And I'm a postdoc at the Museum für Naturkunde of Berlin. And I started my career in Italy, University of Padua, and then moved to Germany first to the Geoscope Museum of Lichtenberg with Sebastian Vogt, and now I'm in the Jörg Frobisch lab working on the Bromacker project, this important continental site of the early Permian. Okay, I'll give you an overview of how footprints and other trace fossils can be used for stratigraphy in the Permian. But I don't see the slides. Okay. So, ichnotaxa that are based on anatomically consistent characters are useful for stratigraphy because they follow the evolution of the producer. And you can see this from this scheme on the right from Yogi Schneider work, where you see the stratigraphic distribution of footprints and producers, which kind of match. And also you see an example of tractor-maker correlation from a publication of Sebastian Vogt et al. 2007. Initially, tetrapod footprints were used in Permian local stratigraphy in France and in Germany. So the first works were by Hélène Berger in France and Boy and Fichter in Germany. And some different biozones were defined using several ichnotaxa, but later it was understood that these ichnotaxa had not really stable basis. So what happened later in the studies of Gann and Duran, 2007 for France, and Vogt 2012, They revised the ichnotaxonomy, and they saw that these previously defined biozones were like baseless practically. So they identified a signal, but it wasn't supported by ichnotaxonomy, and so all these biozones were actually less than previously thought. This was a problem of the triple footprint ichnotaxonomy for the whole last century because the taphonomy of fossil footprints wasn't considered properly. So 150 ichnogenera were introduced by an estimation of Hubble 2000. And by the most recent studies, which are actually impressed by me and colleagues, the valid ichnogenera for the Permian are 22, so that's a very different number and changes things also for biostratigraphy, of course. Local biostratigraphic scheme based on footprints were proposed several times. For instance, in Italy, work of Conti Avanzini. In the United States by Lucas, also by myself and colleagues in South Africa, for instance, and correlated with the stratigraphic scheme of tetrapods. So what we came to understand is that footprints in Permian are widespread and abundant, often much more than skeletons. So, and the ichnofaunal changes are often time equivalent, so they can be good stratigraphic markers. And so chronostratigraphic schemes were produced. This was done by compile all the data on ichnotaxonomy, anatomy-based ichnotaxonomy, and correlating the continental units as best as we can. So using intercalation with marine units and the radiometric cages and other stratigraphical tools. Some characteristics of tetrapod footprint cross-stratigraphy. There's generally a low resolution because several track makers can produce the same track. So usually when we talk about an ichnotaxon, like an ichnospecies can be done by an entire family of producer, for instance. So the ichnofaunal turnover is lower than the faunal turnover of the producer, but the stratigraphic resolution of continental stratigraphy is low, and also skeletal sites are not as many as footprint sites. So we can still build a meaningful chronostratigraphy out of it. Lucas in 2007 introduced two biochrones from the Permian, an early Permian Dromopus biochrones and a late Permian Rhynchosauroides biochron, mostly based on the second on Italian ichnoassociations, but there was a gap in the middle Permian. Later, Vogt and Lucas in 2018 revised the chronostratigraphy of the Permian and kept the Dromopus biochron and assigned to Axelian Artinskian age, introduced the Herpetopus biochron for the interval between Congorian and Guadalupian, and introduced the Paradoxicium biochron for the Lopingians, so in replacement of the Rhynchosauroides biochrones. And later in the work by Yogi Schneider et al., these boundaries were slightly changed based on a revised stratigraphy. In work with colleagues, I introduced a sub-biochron of the Herpetopus biochron by studying some mid-Permian associations, and this would correspond to the Guadalupian. And later, I introduced also other two sub-bicrons for this Herpetopus bicron, the Dicynodontippus, that would be from late Capitanian to early Buchapingian, and the Herpetopus for the Congurian. Okay, let's see. The next. In the most recent work, which is a chapter of regarding footprints, ichnotaxonomy and other features, I revised also with colleagues the chronostratigraphy of tetrapod footprints, and I transformed the sub-bicrons in proper bicrons. So now there will be 5 footprint bicrons for the Permian. So the Dromopus that starts in the late Pennsylvanian, in the Casimovian, and reaches the Middle Artinskian. Then Herpetopus bicron from Mid-Artinskian to base of the Rhodian. Brontopus, which is basically from the Rhodian to the late Capitanian. The Synodontypus from late Capitanian to mid-Vucapingian, and then Paradoxicnium for the rest of the Permian until the Induan. As you can see here, there is a wide distribution of footprint sites, but they're more localized in low latitudes in the early Permian, in the lower Pangea scheme. And they are more widespread, although rarer in the mid-late Permian in the upper Pangea scheme. And we see from studying the association that the ichnofaunal events correspond to the faunal events that we observe in skeletal records, such as the Artinskian warming event and the Dinocephalian extinction. What about other vertebrate race fossils? Coprolites have been already used in local biostratigraphy by Hunt et al. 2005. You see a scheme on the left from North America, Cisuralian. Vertebrate burrows also show morphological differences through time. So there is potential for biostratigraphy and chronostratigraphy, but more occurrences are needed, more descriptions, and especially ichnotaxonomy to be used as stratigraphic markers. Invertebrate trace fossil can be also a tool for biostratigraphy, but they're strongly facies dependent. There is a very slow ichnofaunal replacement, so that's not really good for stratigraphy. They're difficult to correlate with the producer. And so far, only a few cases can be useful in stratigraphy. One example is Ferrapus, that was used by Lucas et al. And Switcha, but there could be more. So for future perspective, the correlation between continental and marine succession should be strengthened, and the paleobiogeography should be taken into account more in detail. Then the tetrapod footprint chronostratigraphy should be improved by the use of ichnospecies, because so far was based on ichnogenera, which were taxonomically more stable at the moment. And a chronostratigraphy of vertebrate coprolates and burrows might be developed by new description, new occurrences, and new ichnotaxonomy. And also should be understood which invertebrate trace fossil could have a meaning for biostratigraphy.
Good morning, good afternoon, good evening. Let's see. So I'm going to be sharing a bit of work that I have been doing with Merland and Estelle. Merland was my PhD advisor, and I don't know if he's in the meeting or not. I think he was going to try and make it, but we'll see. And one of the many things I inherited from Merland while working with him, because we continue to work together, was his fondness for accreted terrains. And so this essentially started as a sort of postdoc project for me. I did my PhD work in northeastern Nevada in Elko County, not far from the Pequops, actually, the Spruce Mountain Range, just to the west of the Pequops. And so I'm excited to get back out to Nevada with Lucia and Charles next month and collect some fuselinids. And I initially started out as a cononaut worker, and then Merlin said, well, you really need to be looking at the fuselinids too. And I begrudgingly accepted that. And now these days I do significantly more fuselinid work than I do cononaut work. And so he sent me up to British Columbia to recollect some material that him and the late Ted Danner collected back in the early 70s, I believe it was. And it's a really interesting area. You can see a photo. I'm assuming y'all can all see the slides. Yes, okay. And so there's these kind of low, crummy outcrops in this area near Meadow Lake, where there's actually a very abundant assemblage of fuselinids that span from Moscovian age, so Middle Pennsylvanian, up to the Assalian. So if you're not familiar with the terrains of Western North America, this is in British Columbia, so far Western Canada. This area is not far from Clinton, which is about a day's drive for Charles, something like 9 hours from Calgary. And we're in the southern portion of the Cache Creek terrain, which is this sliver bounded to the east by the Quesnel terrain and then to the west by the Stikine terrain. Now, there are a few different models proposing exactly how these coalesced and became the so-called ribbon continent. I'm a pen-headed biostratigrapher, not a paleogeographic modeler, so you can take your pick among those. But it is an interesting terrain in that it is the most exotic of all these terrains that we see here. The southern portion is where we're working, really in the southernmost portion. And then there is a sliver of it that goes up into the Yukon as well. But it's really got significant heterogeneity to it. And that's why we refer to the Cache Creek as a complex rather than a lithostratigraphic group. Because in addition to the carbonates, which I'm studying, there's also ribbon cherts, there's argillaceous rocks, volcanics, intrusives, and then even some ultramafics, little bits and pieces of ophiolitic material. Now, the Cache Creek has been interpreted to be the most exotic, the most far-traveled of the western accreted terrains for some time, and really fuselinids of an exotic affinity, of a paleotethyan affinity, were recognized as being out of place, bizarre, in these rocks of both Ciceralian and Guadalupean age. This predates our understanding of tectonic theory by quite some time, but there was really, not a suitable explanation for it, other than migration, of course. And so Merlin was kind of a significant role player early on in working with the fuselinids of these accreted terrains, particularly down in Oregon. Now, this SCOTUS map shows Middle Pennsylvanian time because that's where the oldest fuselinids from the Meadow Lake section were collected from. It's really tough to call it a section. It's just kind of a blob. But Moscovian time, the conventional interpretation is that these were essentially seamounts, oceanic plateaus, some sort of bathymetric high feature that were accumulating carbonate mud just in the area of around the South China blocks before beginning the journey, or the Odyssey, as Johnston and Burrell said. This is one of those modeling papers that I mentioned, Johnston and Burrell, 2006, the Odyssey of the Cache Creek terrain. So from Middle Pennsylvanian time through Middle Permian time, the deposition of carbonates dominantly on top of these. And then by the time we fast forward to late Jurassic. There's docking. And the terrain has presumably at this point in time already coalesced with Stikine and Quesnel terrains and docked as that ribbon continent. So here's a closer look at the Cache Creek terrain shown in purple here. There really haven't been all that many fusulinid studies done on the Pennsylvanian and the early Permian fusulinids from the Cache Creek. There's been a lot of focus, or more focus at least, on the Guadalupean faunas. You see a lot about Yabiina and the Marble Canyon succession. And this is not too far where we're working in Meadow Lake from Marble Canyon. But these other three principal studies that include detailed taxonomy are focused all in the same area up near Fort St. James and what's called the Pope succession or the Pope limestone, this portion of the Cache Creek complex. And a lot of that is more or less equivalent to what we have in that it's Middle Pennsylvanian up through Lower Permian. But there's really only one study that has focused on the early Permian fusulinids, and that is Orchard et al. 2001. Rui looked at the fusulinids, but really didn't illustrate. I think maybe there's half a dozen individual specimens and no systematics. And so they weren't fully treated at the time. And I know he's since passed away, and he was working on a manuscript that fully details the fusulinid assemblage from the Pope succession, but he died, and I've seen those plates. There's really great material. I think that Vladimir Davidov has it at the moment. I don't know if he's working on it, but I'd be really interested in seeing what all comes out of that. So here's Meadow Lake, shallow little lake, again, just a little west of Clinton. The mosquitoes in the summertime are absolutely horrendous. I stripped the weatherproofing off of my rain jacket with so much off, which I didn't realize at the time until we got caught in a torrential downpour. The exposures are these little pods of limestone that crop out in this area just along the road. There's really only one significant road cut that catches your eye, and then you start climbing up on top of that and off into these meadows, and you find little low pore exposures of limestone. It's mostly Cenozoic basalt elsewhere in the area. Here's what the exposures look like. This is that one good road cut and my late rain jacket that died shortly after this photo was taken. But most of the outcrops look like this. So nothing too attractive and really no way of easily making heads or tails of this stratigraphically. Now, onto the fusulinids. Now, this is going to get a bit repetitive in that I'm going to be making comparisons back to the same units, the same Paleotethnian units for these correlations. But what's really interesting about this is the repetitiveness of these comparisons. And so the earliest Permian fauna that we found, and I gave a talk on this at Forams over the summer in Perugia and included all of the Pennsylvanian material, but for the sake of the SPS, this is just the Permian assemblage. Pseudoschwagerina moantensis and some little tiny kind of nondescript Pseudochusanella are some of the earliest fusulinids of the Permian, at least that part of the succession that we found, which is very interesting and useful because Pseudoschwagerina moantensis is, at least in some Paleotethnian successions in Japan, is either the nominate or co-nominate fusulinid taxon for the lowermost fusulinid zone of the Assalian. Pseudochusanella is not as useful. These guys didn't really change. They found something that seemingly worked, and so you find very similar morphotypes from the Jalian all the way through the Kungurian. But this is pretty typical for primitive forms of that genus. But it is important that we have this marker taxon, which is similar to Pseudoschwagerina udeni. There's like 13 species in this complex, but it's characteristic of the earliest Permian. Now, I'm going to bounce back and forth and show these comparisons of our Cache Creek specimens, CCT here on the left, with some Eurasian forms, in this case, both forms from the Akiyoshi limestone of Japan, from Watanabe 91 and Toriyama 58. So you can see the pretty remarkable similarity, particularly between the more significant of the two, the marker taxon here, with Pseudoschwagerina muongtensis. More early Asalian, Eoparafusilina ellipsoidalis. It's not necessarily a zonal marker, but it's pretty abundant in Paleotethyan successions, so it does add some additional constraint. It's nice to see there's a couple different morphotypes that haven't really been seen in the Paleotethyan successions, particularly some of these more inflated ones here, but this is the holotype at the bottom from Toriyama. That's again, from the Akiyoshi terrain. There's the repetitiveness I mentioned. But it's a pretty common character in the Spiroschwagerina pavlovi / Pseudoschwagerina muongtensis zone. A little bit younger, mid-Asalian fauna, again with the marker taxa. This on the left is what Kobayashi fairly recently described as Schwagerina watanabei, which was formerly regarded by Watanabe as Schwagerina globulus japonicus, but in that 91 paper, as great as it is, didn't describe. There's really no taxonomy in that paper, and so Kobayashi went ahead and named it after him for elucidating that. And then there's also this form of Alpina Schwagerina, which in that same paper, Kobayashi assigned to Nagatoensis. This is kind of a weird genus that has traits of both Pseudoschwagerina and Spiroschwagerina. It's notably got this very thickened outer wall in the last 2 to 3 volutions. But both of these are very distinct, and you can see here comparisons with a couple of Akiyoshi forms that really illustrate just this amazing similarity between these Cache Creek, and again, these are from South Central British Columbia, and some of these taxa are endemic. If we went back and looked at some of the Pennsylvanian stuff that I have, you'd see things like Carbonoschwagerina morikawa, which is endemic to Japan. Additional mid-Asalian taxa that aren't as biostratigraphically useful. Again, there's Pseudochucinella. This one a little more advanced than the one we saw previously that occurs in the muongtensis zone. Schwagerina crotoi, the subspecies here, caudata, which is fairly typical for Schwagerina in terms of its morphology for this particular interval of mid-Asalian time. And then finally moving into the late Asalian fauna. So this is the youngest assemblage that was collected at Meadow Lake. And this one gave me some trouble. First of all, I got my PhD studying North American fusilids, and so it took me a couple of years to really learn to speak Paleotethyan fusilid. Duolingo doesn't offer that, so it took some time. And not only that, but some of these are difficult to differentiate from even younger forms. There are several taxa that look very close to Schwagerina firma here that might lead you down an Artinskian or even a Kungurian road. And so it was kind of challenging, but actually helping out Charles with some Chinese material kind of got me back on the right track with this. And so I made some minor changes actually to this fairly recently. This is Schwagerina firma. Below is Paraschwagerina longa, which is, in my opinion, kind of a transitional form between Paraschwagerina and primitive Acervoschwagerina. It's got that really wacky septal fluting to it. And then, again, for the sake of comparison, here's a couple of Eurasian taxa, again, from the Akiyoshi terrain, Schwagerina firma, from Watanabe, and then another from Watanabe, Paraschwagerina longa. These are often poorly preserved. For one, they're pretty large, but they're also fairly inflated and kind of flimsy. And so you get partial tests. Sometimes the tests aren't as well oriented, but I try my best to produce well-oriented specimens. And so to conclude this, I've kind of put together this, it's a very generalized correlation in that there are no specifics to it. It is a list of genera, but it does illustrate the correlation potential that we have here because of this very rich fauna. And so it also, this is the same figure from the forams talk, so it does include the Pennsylvanian fauna, going all the way from the upper Moscovian here into about mid-Jalian, and then popping up here into lowermost Assalian. And then with the Schwagerina Watanabe, that Schwagerina zone is recognized elsewhere, but that taxon is not. And then representatives of Paraschwagerina and the Schwagerina firma kind of species complex there in the uppermost Assalian. And so that's what I've been working on. This is one of many projects on the docket dealing with both global correlation using fusulinids, but also dealing with accreted terrains, because Merland has spent his career collecting in accreted terrains and is kind enough to gift me some of that material shortly. So thank you.